Yes, madam. Shall I start?
Start చేయండి.
Oh. So today our class is about multiple integrals. So in multiple integrals, we have double integrals and triple integrals. So already we know that integration. So here double integrals is a integral function with double integral. See here. Uh, so here y1 of x, y2 of x or y limit and x equal to a to b or a constant limit, x limit. So first we have to evaluate um, y limit, y variable first, and then we have to integrate with respect to x. Similarly, see the second one. Here it is x is a variable limit and y is a constant limit. So we have to integrate with respect to x first and then with respect to y. Okay. So at the last we have to integrate with respect to constant limit variable. Okay. So this is the indication. So like that we have to evaluate the double integral. So see the example. Integral 0 to 1, integral 0 to x, e power x plus y dy dx. So here 0 to x is either x limit or y limit. Can anyone respond? So here it is y equal to 0 to x and x equal to 0 to 1. So y is a variable limit and x is a constant limit. So the integral function is e power x plus y. So here we separate e power x plus y is e power x into e power y. So already we know that in double integration we have to evaluate the variable limit first and then constant limit. Okay. So first e power x into e power y. So integral e power y is e power y between the limits 0 to x. So into e power x. Again, after substituting the limit, so what are the substitution? Upper limit minus lower limit. So we substitute these limits in y variable. So that is e power x minus e power 0, that is 1. Okay. Now multiple with e power x. So e power x into e power x is e power 2x minus of already 1 is there. So 1 into e power x is e power x. So the constant limit x equal to 0 to 1. So again we have to integrate with respect to x. Okay, with respect to y is over. So at the last we have to integrate with respect to x. So integral e power 2x is e power 2x by 2 minus e. So after substituting the limits we get the answer. Okay. So like that we have to evaluate in double integral. So here, see the second example, double integral. Both the integral limits are 0 to 1. So, both are constant limits. So, we have to integrate with respect to any variable first, either with respect to y or with respect to x. So, see here, integral 0 to 1, again integral 0 to 1, 1 by root of 1 minus y square dy into dx by root of 1 minus. So, here we separate the functions. So we have the formula from intermediate. So this is sine inverse y between the limit 0 to 1 and sine inverse x between the limit 0 to 1. Okay. So here both are constant limits. So we have to evaluate with respect to any variable first, either y or x, either x or y. Okay. So here we have the formula sine inverse by sine inverse x between the limit 0 to 1. So after substituting the limits, we get the value pi by 2. That is pi squared by 4. And see the third one. So third one also both are constant limits. So integral 1 to 3 is a constant limit or a constant limit, and integral 1 to 2 are also constant limits. So here also we have to integrate with respect to any variable first, either x or y. So we are doing with respect to first x. that is integral 1 to 3 x y square dx. So we separate the function. So that is y square into what is integral x dx? X square by 2 between the limits 1 to 3. Now substituting the limits in x, we get 8 by 2 integral y square dy. Here y limits are 1 to 2. Again integral y square dy is y cube by 3. Limits 1 to 2. So by substituting upper limit minus lower limit in y, we get the answer 28 by 3. Okay. See the fourth one, integral 0 to 2, again integral 0 to x, y dy dx. Here, the first integral is in terms of limits in terms of y. So here y equal to 0 to x. So we can take y equal to 0 to x and x equal to 0 to 2. So finally, y are variable limits and x are constant limits. Understood? So that is integral y dy is y squared by 2 between the limit 0 to x into dx. Again, by substituting the here upper limit is x, lower limit is 0, that is x squared minus 0 into 1 by 2. Again, we have to integrate with respect to x, that is already 1 by 2 is a constant. Integral x squared dx is x cubed by 3 between the limit 0 to 2. By substituting the limits, we get the answer. Okay. Like that, we have evaluate double integration. And see this here, some more problems 5, 6, 7, same model. Um, so this is left for you. And 8, see the eighth one. So integral 0 to infinity, again integral 0 to infinity, e power minus of x square plus y square dx dy. So this is an important result. So directly we do this. Or here there are two methods. So we can follow any one of the methods. So integral 0 to infinity e power minus y square. So here we have the direct formula, integral 0 to infinity e power minus x square dx is root pi by 2. Like that, integral 0 to infinity e power minus y square dy is also root pi by 2. So by multiplying these two, we get pi by 4. An alternate method is, so here our multiple integral double integration, in, the integral function is in the form of Cartesian coordinates x and y. So here we changing into polar coordinates, that is r and theta, that is integral 0 to pi by 2. So why? Because the polar coordinates are r and theta. So here theta varies from 0 to pi by 2. See this diagram. Okay. And r are varying from radius 0 to infinity. So integral 0 to pi by 2. Here also r limits are constant limits and theta limits are also constant limits. So we have to integrate any variable first, either r or theta, or theta first and then r next. Okay. So integral 0 to pi by 2 e power minus r square. So we have to integrate e power minus r square. So by doing this double integration with constant limits, we get the answer pi by 4. So the first method answer is also pi by 4. Okay, so we can follow any one of these methods. Next, see the ninth one. It is also very important. So in the last years, one of the years they may be asked. So integral 0 to 5, again integral 0 to x square. So what are the variable limits here? Y equal to, we can take y equal to 0 to x square. So y is the variable limit and x equal to 0 to 5, it is a constant limit. Okay. So we have to integrate y with respect, so we have to integrate first with respect to y and then x. Next. Mm, here, so in the previous problems, we have to evaluate the double integral with some constant limits and with variable limits. But in this case, to evaluate double integral, xy into x plus y dx dy over the region capital R bounded by the curves are y equal to x square and y equal to x. Okay. So see this here there are no limits. Only the integral function is xy into x plus y dx dy. So from this given curves we have to get the limits. So the curves are y equal to x square and y equal to x. So we know that y equal to x square is one of the types of parabolic curve and y equal to x is a straight line. We know that. So from these two curves, so we get the point of intersection 0 comma 0 and 1 comma 1. Okay. So next, from these also, we get the one variable limit and one constant limit. That is either x or y. So integral 0 to 1, again integral. So we have to take, it should be like that one is a variable limit and another one is a constant limit. So further we take y equal to x square to x and x equal to 0 to 1. So why? Because see this diagram. So it is a parabolic curve y equal to x square and x equal to y is a straight line. So these two curves, the point of intersection region is this. Okay. So the point is 0 comma 0 and 1 comma 1. So we have to take one variable limit and one constant limit. So, so generally we take um, from lower curve. What is this curve? Y equal to x square. So from this lower curve we get y equal to x square, and from this upper curve y equal to x. Okay. So generally we take from lower curve to upper curve. Whereas in or change of order of integration, we take from upper curve to lower curve. Okay. So here y varies from x square to x. Are you understood? So up from the lower curve, we get y equal to x square. From the upper curve, y equal to x. So we take from lower curve to upper curve. So that is y equal to x square to x. And the remaining one of the remaining limit is the constant limit. That is x varying from here x coordinate is 0, point of intersection, and here this point the x coordinate is 1. So x varying from 0 to 1. Okay. So here we have to integrate y with respect to y first, and then with respect to x. Okay. We can also take here we take y equal to x square to x. We can also take x is a variable limit also. So if suppose from this lower curve, what is x? Root y. From this upper curve, what is x? Y. So we can also take x equal to root y to y. And remaining y is a constant limit. Okay, now we can interchange. So it should be like that. One of the in both the limits, one it is variable limit and other one is constant limit. It is important. Okay. So we have to integrate the variable limit first and then constant limit. Next, like that. In evaluation of double integral in polar coordinates also, polar coordinates means r and theta. So here also, see this 11th problem, integral 0 to 1, again integral 0 to pi by 2, or sine theta d theta dr, polar coordinates. And both the integral limits are constant limits. So we take r equal to 0 to 1. So we should take theta is equal to 0 to pi by 2. We can't take r equal to 0 to pi by 2. So that is theta equal to 0 to pi by 2 and r equal to 0 to 1. So we can integrate with respect to any variable first, either r or theta. So here we integrate with respect to theta first and then r. So integral sign is minus cos and minus r into, by substituting the limits, cos pi by 2 minus cos 0. So finally the integral function is in r dr. Again integral r dr is r square by 2 between the limits 0 to 1. By substituting the limits we get 1 by 2. Okay. So like that. Next, see this. calculate. Here also, evaluation of double integral in polar coordinates over the area between the circles r equal to 2 sine theta or equal to 4 sine theta. Okay. So in the previous problem we discussed already. So they didn't give directly limits. So from the given curves we get the limits. Like that in polar coordinate also, from these two curves we get the limits. So that is integral. These are standard. So first draw the curve. R equal to 2 sine theta means, so here there is no diagram. So but assume that. So R equal to 2 sine theta. Just consider a rough diagram and R equal to 4 sine theta. So these two curves are different. Okay. So in first curve 2 sine theta, in second curve R equal to 4 sine theta. So there will be some difference. So total curve between the circles, so the theta varying from 0 to pi and r equal to 2 sine theta 4 sine theta. So obviously r equal to 2 sine theta is a lower curve. Um, r equal to 2 sine theta to 4 sine theta, the point of intersection region is in between 2 sine theta and 4 sine theta. Okay, so we take r equal to 2 sine theta as a lower limit and r equal to 4 sine theta as a upper limit. So first we have to integrate r first and then theta. So why? Because r is a variable limit and theta is a constant limit. So we get the answer 45 pi by 2. Next, evaluate the integral by changing into polar coordinates. So here it is. Um, the given the integral function is x square plus y square dx dy. So it is in completely, we know that. So the given region is in first quadrant of the circle. So by changing into polar coordinates, that is x equal to r cos theta, y equal to r sin theta, dx dy is r dr d theta. This is standard general equation. Okay. By substituting in this, so here r is varying from 0 to a. Why? Because here the circle equation x square plus y square equal to a square. R is varying from, so in both the limits from the given question, it is varying from 0. So therefore, r varies from 0 to a and theta varies from 0 to pi by 2. Why? Because it lies in completely in first quadrant of the circle. So by evaluating the variable limit first, so we change integral 0 to a. So integral 0 to a, again integral 0 to root of a square minus y square. The integral function is x square plus y square dx dy. By changing from Cartesian to polar coordinates, x square plus y square is r square and dx dy is r dr d theta. R limits are 0 to a, theta limits are 0 to pi by 2. So finally we get pi a power 4 by 8. And 15th one is left for you. Please try. Next, change the order of integration. So already I told you, in change of order of integration, we take the point of intersection region and we should take the limits from upper curve to lower curve. So it is important point. So from this question, x y varies from x square to 2 minus x and x varies from 0 to 1. So first we draw the curves y equal to x square and y equal to 2 minus x. So this is the diagram. Please see that. So the line y equal to 2 minus x passes through this. So these are the point of intersection for these curves. And solving these two equations, so we get the limits, that is x equal to 1 minus 2. If x equal to 1, y is 1. If x equal to minus 2, y equal to 4. So the point of intersection of the curves are, so again we have the 2 points. Okay. So here we split the region, we split the integrals along OACO xy dx dy, next CABC xy dx dy. So this is the diagram. So here we split into two parts. Okay. So in the first integral, x varying from 0 to root y and y varies from 0 to 1. Here it is x is a variable limit, y is a constant limit. In second, we split it. So x is also varying from 0 to 2 minus 5. X is a variable limit and y is a constant limit. So here also, in evaluation of double integral, we have to integrate with respect to variable limit first and then constant limit. Next, triple integral. Um, if x and y, x1, x2 are constants, y1, y2 are functions of x, z1, z2 are functions of x and y. So triple integral means triple. Okay. Previously we discussed double integral. Like that, here also triple integrals. So see this example, see this main definition. Here z is a function of x and y is a function of x, and x is a constant limit. So we have to integrate first with respect to z and then y at the last x. Okay. Next, see the first problem. In this problem, all the integral limits are constants. So we have to integrate with respect to any variable first, either x and then y and then z. Or first we have to integrate with respect to y and then z at the last x. Any variable. Why? Because both the all the integral limits are constant limits. So here they take integral 0 to 1 dx, integral 1 to 2 dy, integral um, xyz here. So here they integrate first with respect to z. Integral z is z square by 2 between the limits 1 to 3. By substituting the limits, we get this step. So after that, they can do the integration with respect to y at the log x. Okay. Next, here, see the second example. Um, First, x minus z variable, lower limit is x minus z, upper limit is x plus z. So here y equal to x minus z, y equal to. So first we have to integrate with respect to y and then x and then z. Okay. See this difference. Next. Fourth one is very important. Integral 0 to 1, integral 0 to root of 1 minus x square, integral 0 to root of 1 minus x square minus y square, x, y, z, dx, dy, dz. Okay. So integral x equal to 0 to 1. Clearly we can see that in third integral it is in a function, it is a z. So z, we know that. So clearly we can tell z is varying from 0 to y because z is a function of x and y from the definition, and y is a function of x and x is a constant. Okay, clearly we see that z is varying from 0 to root of 1 minus x square minus y square, and y is varying from 0 to root of 1 minus x square, and x is varying from 0 to 1. So here, what are the variable limits? Z and y. So from these z and y also, first we have to integrate with respect to z and then y at the log x. Okay. So x, y. So integral z is z square by 2. Now the substituting the limits 1 minus x square minus y square. Okay. Next, so total it is converted into y, that is x into 1 minus x square into y square by 2. Again we have to integrate with respect to y, that is y square by 2 minus y cube by 4. So again substituting the limits in y, we get this. Okay. Next, at the last we have to integrate with respect to x. So totally it is a simplification. You have to do this. First of the main points are in double integration also, in triple integration also, we have to integrate uh, variable limit first and then constant limit variable. Okay. Next, change of variables from Cartesian to spherical. So our question is in xyz. So we can change the variables from Cartesian to spherical polar. So what are the spherical polar? Rho, theta, phi. or simply we can take in the place of rho small r we can take. So r theta phi. So these are standard general equations. So this is Jacobian. So ds dy dz is we can take Jacobian dr d theta d phi. So already we know that the Jacobian definition dou x by dou rho dou y dou x by dou theta dou x by dou phi. Similarly, dou y by dou rho dou y by dou theta dou z by dou phi dou z by dou rho dou z by dou theta dou z by dou phi. So by expanding this determinant, we get the value directly. So it is need not to simplify. Directly we note that Jacobian value is r square sine theta. Why? Because these are the standard general equations. Okay. So changing from Cartesian to cylindrical coordinates also. So whereas in spherical coordinates we have rho, theta, phi. In Cartesian from Cartesian to cylindrical coordinates we have rho, theta, z. Okay. So this is the evaluation. So you have to know this triple integral f dx dy dz is in the place of x we write rho sine theta cos phi, in the place of y rho sine theta sin phi, in the place of z rho cos theta, and dx dy dz is rho square sin theta. Okay. In the place of rho we can take small r also. Like that cylindrical coordinates also, this is the main important formula. Okay. So see this problem, evaluate this triple integral over the volume enclosed by the sphere by transforming into spherical polar coordinates. So in the question they mention spherical polar coordinates. So we have to convert from Cartesian to spherical. That is x equal to odd sine theta cos phi, y equal to odd sine theta sin phi, z equal to odd cos theta. And we know that in the previous mm, in the previous page, we discussed the Jacobian r square sine theta. So like that, and these r theta phi limits are also standard. So r varying from 0 to 1, theta varying from 0 to pi, phi varying from 0 to 2 pi. Okay, so you just remember that. And evaluation of triple integral. So all the three integral limits are constant limits covered. So we have to integrate any variable first. So here they integrate with respect to r and then theta at the loss phi. So integral here it is r power 4. So integral r power 4 is r power 5. And next by substituting integral 0 to 1 in r. So 1 by 5 integral sign is minus cos between the limit 0 to 5 remaining d phi. And integral 1 d phi is 5. So 2 by 5 into 2 pi 4 pi by 5. So like that we have to evaluate. Next, change of variables from old variables to new variables also same. So we have f of x comma y and new coordinates are u comma v. Okay. So these are the main points. Applications of integration. Next, Taylor series and Maclaurin series. So we know that Taylor series in the previous classes we discussed Taylor series and Maclaurin's in single variable. So this is double variable. Sorry, this is the single variable. F of x equal to f of a plus x minus a into f dash of. You know this. So this is a Taylor series expansion of degree n about x equal to a. In the place of a we have 0 if in the place of a if we have 0, it is a Maclaurin series. Okay, that is f of x equal to f of 0 plus x into f dash of 0 and so on. So this is Maclaurin series about x equal to 0. Maclaurin series expansion about x equal to a. Taylor series. Maclaurin series is about x equal to 0. Okay. See this problem. Obtain Taylor series of the function sin x in the powers of x minus pi by 4. So Taylor series expansion of f of x in the powers of x minus a is given by. So we know this series and our function is sin x and a is pi by 4. So this is the expansion. So here in this expansion we have the derivatives. First derivative and second derivative. So what is our function f sin x? F dash is cos. F double dash is minus sin. So like that we have so on derivatives. and substitute the value a, that is pi by 4. Sin pi by 4 is 1 by root 2, cos pi by 4 is the differentiation of cos, sin is cos, and cos pi by 4 is 1 by root 2. So now substituting the a value, we get the derivative value. So finally, the Taylor series expansion is sin x equal to. We substitute in the Taylor series expansion, we get this series. Next, so we can also expansion of e power x about x equal to minus 1. So alternate method is there. Let x plus 1 equal to t, x is t minus 1. So our function is e power x. So by substituting x value is t minus 1, that is e power t into e power minus 1. And e power minus 1 is 1 by e, and the expansion of e power t is 1 plus t square by 2 factorial and so on. At the last, we replace t. What is t? X plus 1. Okay? So we can do this problem in Taylor series expansion also by taking it. Okay? Next, Maclaurin series is simply we take in the place of a 0. We take small a equal to 0. So they ask the question expansion of cos hx, Maclaurin series. So we take a equal to small a equal to 0. So what is f cos hx? So we know the hyperbolic function formulas. Differentiation of first derivative of cos hx is sin hx, and second derivative is cos hx. By substituting the a value, that is a equal to 0, we get the Maclaurin series expansion. So this is Maclaurin series expansion. You know, next, last, Taylor series for function of two variables. So in the previous we discussed the single variable, Taylor series and Maclaurin series for single. Here it is the function of two variables, that is f of x comma y, that is f of a comma. So this is the main formula, series formula. So you have to remember that. And here if a equal to 0 and b equal to 0, if we put a equal to 0, b equal to 0 in Taylor series, directly we get the Maclaurin series of function of two variables. Okay? Series example, expand this function. So here it is a function of x and y, in both x and y, in the powers of x minus 1 and y plus 2. And what is a here, what is b here? A is 1, b is minus 2. And expand this function up to terms of third degree. So we have to expand the series up to third degree, third derivative. So x equal to, sorry, a equal to 1 and b is minus 2. So first we have to take derivatives. So this is f, our given f. So from this partial derivative with respect to x, that is x square y. So we have to differentiate with respect to x. So we get the value 2xy. So why? Because differentiation of x square is 2xy. So while differentiating with respect to x, we treat y terms or constants. While differentiate with respect to y, we treat x terms or constants. So this is main point in partial differentiation. So, so we have the derivatives. So fy of x comma y is, so partial differentiation with respect to y, x square y plus 3y minus 2. Okay, so we have to differentiate with respect to y. So means x is a, we treat x is a constant. That is x square into 1 plus 3 into 1 minus 0. That is x square plus 3. And f xx means we have to differentiate x two times. Already we have done first derivative with respect to x. So here again we have to differentiate. That is dou square by dou x square of f of x comma. So like that fxy, fyy and f triple x, triple y, fxxy, fxyy, and substitute in the Taylor series. Okay, so this is Taylor series of function of two variables. Okay. So here we first term is f of a comma b. So here a is 1, b is minus 2. After substituting the functional value, we get minus 10. So by substituting in the series, we get minus 10 plus x minus a is 1 and f dash of fx of a comma b is fx of a comma b is minus 4. So by substituting these derivative values, we get the series. Okay. So this is a Taylor series of function of two variables. So here it is one main point is, so fx means we have to differentiate with respect to x, and fy is dou by dou y, and fxx is 2 times partial differentiation with respect to x, and fxy means already dou f by dou y we done. So that is again for that function we have to apply dou by dou x, that is fxy. And fyy means 2 times partial differentiation with respect to y. And fxxx means already we done fxx. Again we have to differentiate with respect to x for this. Okay. And so like that we done partial derivatives and substituting in the Taylor series. Okay, understood? Yes? Anybody? So these are all about evaluation of double integral and triple integral and Taylor series for function of single variable and function of two variables. So you have to remember this series. Okay. About x equal to a means a Taylor series, and about x equal to a equal to 0 means it is Maclaurin series in single variable. Whereas in function of two variables, about x equal to a, y equal to b means it is Taylor series, and a equal to 0, b equal to 0. If we put a equal to 0, b equal to 0 in Taylor series, directly we get Maclaurin series. Okay, is it clear? Please respond. Yes, Kokila. H1. Is it clear or not?